Okay, now it's recorded. So welcome to this lecture. Okay, if anything, just interrupt me because I will not see the Google Chat often. Okay, because I'm lecturing. So chapter 1, introduction to system and signal, part 1. Okay, so you have a lot of part later on. So this is me. Okay, when you click later on this one, this link, it is linked to my UTM profile. Okay. So I've been asking you guys why you need to study signal. Okay, I give a padlet because when we need to have, even though this course is compulsory, I know, but we need to know the purpose of why we are studying this course so that we will appreciate this course better. And actually, only then you understand the purpose, then you can learn better, and because you know what's the point of studying, something like that. Okay. So without further ado, okay, what is system? So system is actually a signal processor that can either modify the signal or extract further information from the received signal. So if you guys see here, there is a box, okay? There is a black square box. So system is like having an input, an output, and some transformer in the middle, okay? That's why, in other words, it is a generator of signal, or it is a transformer of signals, okay? So you have transformer, okay? Because input will undergo output, will undergo transformer, and transformer will change the output, and will change or not change the output. So your output can be exactly as your input, or can be exactly opposite, or exactly in different form, exactly in different form compared to your input signals. Okay, so we have a system have minimum of one input and one output, but of course we can have many. We can have two input and one output, or we can have one input, two output. Okay, so introduction, this course is about signal and their processing by system. So it involves physical signal by mathematical function. Okay, by mathematical function. Or modeling of physical system by mathematical equation. So it's different. Okay, I make it highlight here, or so that student can see. Otherwise they say, Raimi is totally the same word. Okay. Okay. So why study signal system? Okay, this is a fundamental to all engineering. Okay, step involved in signal system are model system, analyze system, design system, and implement. Okay, so involve writing a mathematical description of input and output. Okay, so just like, for example, digital electronics. Okay, this is totally different thing, but you need to know the input signal, input variable like A, B, C, D. Then you will know your outputs, right? Maybe your transformer, what your transformer is, example, AND gate, OR gate, something like that. That will change the inputs. Okay, I mean that will do some transformation on the input, so that your output will be the as desired, as request. Okay, then you model the system. Okay, analyze system, and design system. So when we do as an engineer, when we want to design something, okay, we have certain parameters that we want. Okay, so that's why design is being used also in design system, because require design system on suitable system architecture, as well as finding suitable system parameter. Let's say you want this system, this design to work based on this performance. So you need to set which parameter to be controlled, which parameter to be achieved in order to have that performance. Okay, so implement system, test and system, check system and the input and output signal to see that the performance is satisfactory. So what is signal? Seems simple question. What is signal? Okay, so signal represented as a function of one or more independent variable. Okay, it can be one, for example, y equals to x t, or y equals to x t plus z t. Okay, it is something that represent information. Okay, we have some information inside our signal, just like your handphone. Okay, when you browse Wi-Fi, right? I mean, when you browse internet, you have Wi-Fi signal. Inside that Wi-Fi signal is actually packet of data. you have data inside, information. Let's say you want to surf for Facebook, whatever, right? So inside signal is information of Facebook. Okay. Example, temperature at designated points. Example of vibration of rectangular membrane function of two special variables. Okay. So signal can be both natural and man-made. Okay. Man-made is normal. Can you guys, I think my previous students know that I like to call names. Okay, so what is do you think is the natural signal? Who is the lucky person? Okay, Joseph, what is the? Can you give me one example of natural signal? Joseph, can you give
Yes,
me
doctor. Excuse me.
one
Example
example
of what?
of natural signal? Man-made signal, everyone know Wi-Fi, but how about natural signal?
Natural signal example, yes.
Yes. Can you give example?
Sound.
Yes. Oh,
Sound.
yes. Good. Sound. Speech is our signal, audio signal. Okay. Thank you.
Yeah.
What? Satya. Other than this audio signal, what else is natural signal? Example, Satya. Satya, what can you give me one example of natural signal, not man-made?
Heartbeat, doctor.
Yes.
Heartbeat.
Yes, heartbeat. Okay, good. Heartbeat. Okay, and then I think maybe you guys, all of you aware, like neuron. Okay, neuron is signal also, but it's a bioelectrical, something like that lah, biochemical, but it's signal also, the one that happening 24/7 inside our brain. Okay, thank you, Satya. So you see, now we go to the type of signals. Okay, type of signal, we have continuous time, discrete time. So you see the word here, continuous time, discrete time, means there is different in the nature of the signal in time aspect. Okay, then we have analog and digital signal, energy and power signal. Then we have deterministic and probabilistic signal, and we have harmonic signal, and we have even and odd signal. Okay, deterministic is you can know this nature of signal, means can be determined. Probabilistics is is random, you can know by probability. Okay, but you cannot know for sure. Okay, harmonic signal is repeated signal, is repeating. Okay, and then you have even and odd signal, which one is symmetry and one is anti-symmetric. Okay, if you have question, just interrupt me. Okay. So we go to the continuous and discrete signal. So continuous time signal is defined for all value of t. Okay, if you can see here, example, you can see this is our horizontal axis is correspond for time. You can see that the signal is actually continuous. Okay, there is no gap. So means that all signals, I mean at any time there is signals. So this is continuous time signals. In contrary, for discrete time signal, okay, it's only defined at discrete independent variable time t. So you can see here, right? You can have value of signal at 0.1, 0.3, 0.2, 0.4, and so on. But you don't have value of signal at 0.05, 0.05. You don't have. Okay, here. So this one is a discrete time signals. Okay, I think the figures are very self-explanatory. Then you have analog signal and you have digital signal. This one, if you take digital electronics, is already familiar. So signal with amplitude which can take any value in continuous range, means analog signals we can have value can have many value like 1, 2, 3, 4, 5. within amplitude, for example, within time 1 maybe have 1 amplitude 1, time 2 have amplitude 3, and so on. Okay, it can have any values. Okay, amplitude of an analog signal can be of infinite value. Okay, in contrary with digital signal, which you guys familiar only, we only have certain value. For example, if you want to take higher logic gate, for example, as if you want to take 1 0, okay, so you only have 1 0 1 0, something like that. I think you guys familiar already. Amplitude of digital signal take value from a discrete set. Okay, discrete set, for example, you want to consider 5 volt to 10 volt is represent as binary 1, and 5 to 0 is considered as binary 0, and 0 to blah 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 is negative, is don't care condition. Okay, do you guys understand me? Google chat, do you guys respond? Do you guys understand what so far?
Yes, doctor.
Only one understand, the other don't know what happened. Maybe drinking Milo. Okay, thank you. Okay, thank you for responding in Google Chat. So now we go for these 4 figures. Okay, we go to these 4 figures. Okay, you can see the nature of figure A. You can see this is analog signal, certainly, because it have values of amplitude. Okay, very means you don't have discrete value. You can have continuous. You have many values, and then it's time continuous. You don't see any gap. So this is analog signal and time continuous. This one is digital signals. Okay, you can see 1 0 1 0. I mean, sorry, you can see 3 negative 3 3 negative 3, for example. Then it's time continuous. You didn't see any time gap. Okay. Then graph C is analog signal, where you can see have a lot of variation of value of ft, of amplitude. However, in terms of time, it is discrete. You can see. Okay, you can see it doesn't have all value of signal at all value of time. Okay, and the last one is digital signal. You can see negative 3, you can see 3 negative 3, so on. However, it is also time discrete. Okay, because we don't have all the values for all for all time. Okay, for all the times. Okay, now we go to the next one, is the power and energy signal. So power signal can be come into power and energy signal. So energy signal is a signal which has certain value of energy. So energy is a measurement strength of signal. Let's say we want to know, let's say, oh, Wi-Fi signal tak bagus lah, Wi-Fi signal is low lah. So this is Wi-Fi energy. Okay. So energy is the area under the squared signal. Okay, so you can see EF, integration of infinity, negative infinity, and you have the squared here, NDT. So this one is already squared, non-periodic signal, deterministic signal. So do you guys know why we actually use squared signal? We didn't use why we must squared the signal? Do you guys know or not? Why do we must square the signal? Because let me see. Okay, so you see, naturally, for example, you have signal. Okay, you can have positive, negative. Okay, positive, negative, right? If we didn't square, okay, and if we want to calculate for energy, for example, it will cancel out, because one is positive, one is negative. You know, because this one is equivalent this one equivalent this one, so it is negative. But if you take what we call it, if you take square, okay, it will be like this. So all of them positive, so there will be no cancel out. This one cancel out because one positive, one negative, one positive, one negative. So in the end, energy 0, something like that. Okay, so is it do you guys understand why we square it?
So, doctor, it should all of this, it's positive.
Sorry?
It should be positive.
Yes, that's why we use square.
Okay.
Okay, that's why we use square, and we must use square, otherwise it will be cancelled out. Okay, then okay. So power signal is a signal with a certain value power and non-zero. Okay, non-zero. So power is a time average of energy. Okay, you can see it's a bit related but not directly similar. Okay, but you can see the equation is a bit related. Okay, so power is a time average of energy per unit time. So when we say time average mean 1 over T. Okay, so that's why you can see here 1 over T. Okay, time average. Okay, then this is T over 2, negative T over 2 means over the complete period. Okay, then we use also here F square. Okay, power is useful when energy signal goes to infinity. For example, periodic signal and random signals. Okay, bunyi kursi, sorry I sit on an old chair, so you sometimes listen to the sound. Okay, so note that power is a time average factor of energy. Okay, energy signal has certain finite value energy and has zero value of power. Okay, so we need to make a differentiation here so that you guys we know. Okay, power is actually here is time average. Okay, is it okay? I make it highlight here so that you guys will see it more clearly, focus. Okay, so here is energy signal. If you guys don't like I'm highlighting, tell me. Okay, I'm highlighting here and I will later on save as PDF. Okay, I'm highlighting so that you guys can focus. Okay, I have no problem. Okay, power signal has certain value of power and has infinite value of energy. In general, signal has certain value in time from negative infinity to positive infinity has an infinite energy. So this one is in general. Okay, in general, we will assume we will take value in time from negative infinity to positive infinity, just like this one, I think. Okay, so you have continuous. Okay, positive infinity and negative infinity. Okay, some signal can be classified neither as power signal nor as energy signal. Okay, some signal they are not energy signal and they are not power signal. Okay, so what are they? For example, for example, you have RAM. Okay, you will study later on a lot of type of signals. Okay, second, the one that is not energy and also not power signal is actually RAM signal. Okay, RAM signal. Okay, this is RAM signal. Okay, this shape. Okay, so it is not energy and this is also not an power signal. Okay. Okay, now next we go to what we call as a periodic signal. Okay, I hope I didn't miss. Okay, listen. So periodic signal is actually harmonic. When we referring to harmonic means that it is a periodic signal. What is harmonic means it is repeated. Okay, so condition for periodic signal ft for any value of positive t, you see here ft plus t and ft plus nt. This one is number of integer. Okay, number of integer. So minimum value for t, minimum value for t, which is the complete periods. Okay, complete period, one complete period, is known as the fundamental period, t naught. Okay, t0 or whatever you call it, but this one is t naught. So we take this minimum value st as we call as a fundamental frequency. Okay, fundamental period, because it's t. But if you say f naught, you can mention it as fundamental frequency. Okay, you may update me later. I'm in the lecture right now. Okay, don't worry. Okay, maybe after 1 or maybe you will contact me at 2 p.m. Okay, thank you. Okay, where was I? Sorry, there's students. Okay, so fundamental frequency, you have f naught 1 over t naught. Okay, this is I think you guys understand already. Okay, frequency is actually 1 over period. Okay, then you are introduced to this equation, which is omega equals to 2 pi f naught. Okay, omega equal to 2 pi f naught, and it is in the radian per second. So you can see here, this is periodic signal because it is repeated. okay, repeated. And this is a periodic signal because you can see it's only one signal there and it is not repeated. So this is a periodic, okay. Next, we go to the deterministic and probabilistic signals, okay. Deterministic from the words mean it can be determined. It can be determined is a non-physical representation, okay. Can be described by analytical expression for all time, for example, past, present, and future. Okay, means you can describe this by analytical expression for time because we can know the time based on the for all time because we can know based from the past event, present event, and future event. Okay, this is just a concept. Okay, just to make you understand. Okay, what does mean that we can know the past, present, future. For example, this is just to make you understand, okay? For example, if you have T here, okay? So you have signal, okay? You have signal, okay? So you have this one, of course, T negative, okay? T negative. This one is also T, this one is of course T positive, okay? Let's say we take this one, let's say we take this one as our present, sekarang, present, now. So this will be our past and this will be our future later on, means this one later on, okay? Do you guys understand this? What does it mean? What does it mean by past, present, and future? Understand?
Understand, Doctor.
Okay. I think early is easy to understand, so it's okay. Then probabilistic signal is signal that is probability. Okay, you can only know its probability representation such as mean value, root mean square. Okay, RMS. So also known as random signal. For example, and then this probabilistic signal cannot be determined accurately. Okay, so example noise just now. Okay, I suddenly have rain in the background. I suddenly have people doing renovations, okay? But let's take the rain example. Rain, we know rain will come, okay? We know rain will come, right? But we don't know when is it going to rain. Am I correct? So rain is one as we can consider as like a noise, okay? So why we noise? I mean, I just want to make you understand the concept of noise. Something that is happening, but we cannot determine accurately, okay? So in communication system, there is a lot of noise, okay? Now we go to the even and odd signal, okay? Even and odd signal. Even symmetrical signals has the same value at time t and negative t for all value of t, okay? So you have ft equals to f negative t. So this is symmetric signal. What does it mean symmetry? You can see, let's take this one vertical as a mirror, okay? As a mirror. So this signal with symmetry at vertical axis. That's why you have this representation ft equals to f negative t. If you have t here 1 at 1 second is equal to 1 amplitude, and here t negative 1 is still equal to 1. So regardless of the time, okay, whether positive, negative, it will display the same amplitude. So this one is an even signal, which can also describe as symmetrical signal at symmetry at vertical axis. And we have odd anti-symmetric signal. Okay, the value of odd signal at time t is negative to the value at time negative t. So you can see here at the time positive, the pair will be negative. For example, if you have t at 1 second is equals to 1, but t negative 1 will be negative 1. Okay, so it will be anti-symmetry at horizontal axis. Never mind. Okay. Okay, so next, skew signal. A signal can also be a skew symmetry. Okay, it looks like symmetry, but it's a skew symmetry here. So you have a negative f and you have t, then you have some period. which is half of the period, okay, which is half of the period. Let's say here 1 second, then you have let's say complete period is 10, so you have 1 plus 10/5, so 6, okay, something like that. Okay, so this is skew symmetry. And then you have here is a hidden odd signal. Why does it mean by hidden? I will mention later on. Odd signal combined with a DC value, not anti-symmetric anymore at, okay, you guys can read this, but I think it better to be explained graphically, means demonstrate, okay. So, okay. So now we look on this hidden odd signal, okay, hidden odd signal. For example, okay, for example, I try to copy paste the slide, okay, because easy for you to refer later on, okay, if I use the same example, okay. Okay, this is shown by example, okay. Now, before this signal, actually, you can see we have a signal like this. But why? But when it become the hidden odd signal is that when we introduce a DC value. DC value is actually a a continuous constant value. For example, here let's say 1, okay, 1. So you add to this, for example, this one is 1 as well. So when you add this one and add, okay, sorry, it's not digital electronic because I want for you to able to see it. See, 1 plus 1. So it will become hidden odd signal because you will increase all of this by 1. Okay, so you have here. So this is 1 plus 1, 2. This one is negative 1 plus 1 will be 0. Okay, so that's why you have here. Sorry, that's why you have here. Okay. Okay, then what else? Okay. Then okay, this where is this? Okay, this one. Okay, so the next lecture is on the time-based operation, time inversion, time scaling, time shifting, all of this, and the rest, okay, will be covered in second lecture as recorded. Okay, so I will share the recorded lecture later on, and I will share the tutorial later on. Okay, because I will record usually at night time. I think Jintong and everyone knows my work. I do late night. Why I choose late night? Because it's night time. No noise. Okay, no background noise, and and during the day I'm a bit busy. So I normally do recording at night time. So please bear with me. Okay, you will have your recorded lecture second. Fully recorded second lecture, okay, so which I will cover the rest of these slides, okay, signal until signal operations, okay, and I will show you the tutorial. So okay, I finish recording. I will share the recording later on. Okay, this is